So we are going to discuss about Alembert's principle. So this is based on Newton's laws of motion. The first law states that whenever a body is in rest or of uniform motion, unless an external unbalanced force acts on the system, it will continue in its state. Okay, so it talks about a state of equilibrium, either at rest, which is basically our static equilibrium condition, or it can be in motion, which is our dynamic equilibrium condition. So we are very familiar with the static equilibrium part. Okay, static equilibrium. We have the basic equations. We know that if an object is at rest and if it is in static equilibrium, we know that it should satisfy the condition sigma fx equal to 0, sigma fy equal to 0, similarly sigma m equal to 0, or this can be generally written as sigma fi equal to 0 and sigma mi equal to 0, where here I represents any arbitrary direction. It can be x, it can be y, or it can be z. Similarly, here I represents any point A, point B, point C. If it is static equilibrium, moment with respect to any point is 0. That is the condition of static equilibrium. But when the object is in motion, okay, we can call the system as in dynamic equilibrium. That's what Alembert's principle talks about. It's basically derived from the second law of Newton, that is we have F equal to ma. Okay, that is the basic condition what we get from the Newton's second law. So Alembert's principle is derived from this basic condition, that is F equal to ma. As per Alembert principle, consider an object. Say I have an object and different forces are acting on it, say F1, F2, F3. Okay, and the effect of these forces is that this object, okay, this object is moving in this direction with an acceleration a. Okay, I use this arrow at the top because acceleration is a vector. Now let's consider there are some angles. Say this angle is θ1 and let this angle be θ2. Let the angle that this F2 makes is 0 with the horizontal. So if we want to write Alembert's equation for this particular condition, it basically says that F equal to ma, right? So where F is the net external force, okay, we will be writing this equation as sigma Fi is equal to mai. Okay, where Fi is the net force in any arbitrary direction I, and mai, m is the mass and ai is the acceleration in the same arbitrary direction which we chose, I. Okay, let this object be having a mass m. Now if you are applying the Alembert's principle for this particular object and considering the direction I as the direction of acceleration, say let the direction be, this be my I direction and let this be my j direction. This is the coordinate system that I'm going to use here. So if I'm considering the I direction, I will be getting F1 cos θ1, which is basically the component. I'm writing the sigma Fi component. Okay, F1 cos θ1, which is in the I direction. Again, F2 is also in the I direction, plus F3 cos θ2. Those are the external forces in the I direction acting on the object that we considered. And what about the force due to acceleration? So A is in this direction, so I'm getting the right hand side of the equation as m times ai. Okay, so sigma Fi, which is this component, can be equated to mai. Now when I try to write the same Alembert's principle in the j direction. Let's see what happens. That's the interesting part. Sigma fj equal to m into aj, right? Sigma fy equal to m into ai, sigma fj equal to m into aj. Now we are going to try this. So first we want sigma fj. So what will be sigma fj? Sigma fj will be j, this upward is considered as the positive direction. So minus f1 sine theta 1. Okay, f1 is like this. So f1 cos theta is to the right, f1 sine theta is downward, which is opposing our positive direction, which is negative. f2 is perfectly horizontal, so we are not going to have any component. Then f3 cos theta is horizontal, f3 sine theta is upward, so theta 2. So it is plus f3 sine theta 2. That forms our left hand side. Now we need to equate it to m times aj. M is the mass of the object, that is m, and we need to consider aj. Okay. When we defined the problem, we said that this object is moving with an acceleration a in this direction. We didn't consider the object moving in the j direction, which means that the object is not moving in the j direction, which means the acceleration in the j direction aj equal to 0. So basically we can write this equation as minus f1 sine theta 1 plus f3 sine theta 2 equal to 0. And when we look closely at this particular expression, this is similar to the condition we wrote here, sigma fy equal to 0. If you are writing sigma fy equal to 0, we will be writing the same equation. As the object is not moving in the y direction, the static equilibrium conditions are valid for y direction. But the object is moving in the I direction, that is the horizontal direction, we need to use the dynamic equilibrium condition, that is Alembert's principle. Okay, and there is one more term we need to know, that is inertia force. Okay, inertia force is the component minus ma. Okay, ma is the mass times acceleration, which is the force, minus ma is called as inertia force. These are the things that are basically required to understand the problems that we had handled using the online test. So now I will explain how each problem can be solved. Already the PDF solution of those are available with you, but those who find it hard to understand the solution process, I will go step by step through different videos.